For Paul Dirac, mathematics was more than a tool. It was devotion. He believed that beauty in equations mattered more than experiment, insisting that only elegance could reveal truth. In a world where physicists chased intuition or data, Dirac stood apart, letting symmetry and abstraction reshape the search for reality itself. But how did this near-religious faith in mathematical beauty overturn the foundations of physics? And what crisis made such a radical solution necessary? In the early 1920s, Cambridge was a place in transition. The Cavendish laboratory, once known for its focus on experiment and measurement, began to echo with a different kind of ambition, a belief that the universe might be grasped not through pictures or mechanical analogies, but through the language of algebra and symmetry. Chalk dust hung in the air as blackboards filled with symbols, matrices, and abstract forms. The old reliance on visual models like orbits and planetary paths gave way to equations that seemed to speak a purer truth. At the heart of this change stood a new generation of theorists. Ralph Fowler, a young professor at Cambridge, championed the adoption of group theory and abstract algebra. He brought the latest developments from the continent into the seminar rooms, translating the dense mathematics of Göttingen and Copenhagen for his students. Under Fowler's guidance, Cambridge physicists began to treat the atom not as a miniature solar system, but as a system governed by hidden symmetries and rules that could be written, manipulated, and revealed only through mathematics. Paul Dirac arrived as a research student in 1923, drawn to this quiet revolution. He absorbed the new methods quickly, learning to distrust pictures and instead to search for patterns and structures that could be expressed with elegance. The Kapitsa Club, a weekly gathering in the Cavendish, became a forum where these ideas took hold. Here, equations were debated as fiercely as experiments, and the promise of abstract algebra, ordering the chaos of quantum phenomena, captured the imagination of those present. Elsewhere in Europe, Werner Heisenberg and Wolfgang Pauli were also turning to abstraction. In letters exchanged across borders, they discussed the power of non-commuting matrices and the strange logic of quantum mechanics. Their correspondence reached Cambridge, fueling even bolder explorations. The shift in Cambridge was not imported wholesale. It grew from within, shaped by local seminars and the persistent questioning of its own students. By the end of the decade, blackboards in Cambridge displayed not pictures of electrons, but dense notations, algebraic structures that hinted at a deeper order. The pursuit of beauty in mathematics was no longer a curiosity. It had become the method of choice for those searching for the laws of nature, setting the stage for the technical challenges that would soon define the next era of physics. The new mathematics brought clarity to the atom, but it also revealed a deep problem. The equations describing electrons, especially those that tried to unite quantum mechanics with Einstein's special relativity, were not working as hoped. In 1926, the Klein-Gordon equation appeared to offer a solution. It was built to respect relativity, treating space and time on equal footing. Yet its structure, with a second-order time derivative, led to troubling consequences. Probabilities, which should always add up to 1, could become negative or exceed 1. The equation failed to guarantee that the total probability remained constant. Physicists recognized the flaw immediately. In quantum mechanics, the wave function's squared magnitude must always represent a meaningful probability, never less than 0, never more than 1. The Klein-Gordon equation's solutions broke this rule. Particles could vanish or multiply without cause. The mathematics suggested a universe where certainty dissolved and conservation of probability, a cornerstone of physical law, no longer held. This was more than a technical nuisance. It struck at the heart of the new physics. If quantum theory could not be reconciled with relativity without losing its grip on probability, then the entire project risked collapse. Some proposed abandoning the attempt, returning to non-relativistic equations. Others tried to patch the Klein-Gordon form, but the repairs only deepened the confusion. The challenge was clear. To move forward, physicists needed an equation that respected both quantum mechanics and relativity, and also preserved the certainty that probabilities would always add up. The answer could not come from tinkering with old formulas. It required a new kind of equation, one that would be first order in time, not second, and that would restore the logical structure quantum theory demanded. As the decade closed, this technical gap loomed over the field. The search for a new formalism became urgent, not just for the sake of mathematical tidiness, but for the survival of the quantum revolution itself. Paul Dirac set out to resolve the clash between quantum mechanics and special relativity, not by patching old equations, but by rewriting the very rules. The challenge was clear. The equation must be first order in time to preserve probability and still compatible with the strictures of Einstein's theory. In late 1927, Dirac began to search for a mathematical structure that could do both. He wrote and rewrote in his Cambridge notebooks, probing the algebraic heart of the energy-momentum relation. The familiar form, E squared equals P squared plus M squared, was too rigid. Dirac asked whether the square root of this relation could be written as a linear operator, one that acted directly on the wave function. The answer required inventing new algebraic objects, matrices that did not commute, but instead satisfied a precise set of anti-commutation rules. These matrices, later called gamma matrices, formed the backbone of his approach. Their defining property was simple but profound. When each matrix was multiplied by another, and that product was added to the product taken in the reverse order, the result was twice the metric tensor of spacetime. This algebra allowed Dirac to construct an operator that, when squared, returned the relativistic energy equation. The wave function itself became a new entity, a spinor with 4 components, each necessary to capture the full symmetry of spacetime and the quantum world. These components were not an optional complication, they were an unavoidable consequence of the algebra and of relativity combined. The theory predicted the electron's spin and its magnetic moment as natural outcomes of the mathematics. In February 1928, Dirac completed his equation. It was concise, first order in both time and space, and its structure was dictated entirely by the demand for mathematical consistency and elegance. Published that year in the Proceedings of the Royal Society, the Dirac equation did more than solve a technical puzzle. It led to the mathematical prediction of antimatter, and it showed that features once thought separate were in fact built into the formalism. For Dirac, this was beauty in its purest form, an equation whose elegance was inseparable from its truth. The Dirac equation, written in 1928, did more than unify quantum mechanics and relativity. Its structure quietly demanded a world with more than just electrons. The mathematics offered 2 branches, one for positive energies matching known particles, and another for negative energies which seemed unphysical at first glance. Dirac, searching for meaning in this symmetry, proposed that these negative solutions hinted at something real, a mirror image of the electron with the same mass but opposite charge. He called it a positive electron, though the name positron would come later. For years, this prediction remained a mathematical curiosity. Some physicists doubted that such a particle could exist, while others found the argument compelling for its elegance. The question lingered: Could the universe truly be so symmetrical, so faithful to the demands of a beautiful equation? In August 1932, evidence arrived from an unexpected direction. Carl Anderson, working at Caltech, was studying cosmic rays with a cloud chamber placed in a strong magnetic field. On a photographic plate labeled number 66, he found a track that curved in the opposite direction from any known electron. The particle had the same mass as an electron, but carried a positive charge. It behaved exactly as Dirac's mathematics required. The evidence pointed clearly to the positron. The discovery of the positron was not just a triumph for experiment, but a vindication of the idea that mathematical beauty can predict features of nature before they are observed. The negative energy branch of Dirac's spectrum was no longer an abstraction. It gained substance in the thin vapor of a cloud chamber, confirming that the universe sometimes follows the logic of symmetry written on a blackboard years before. Today, physicists still chase symmetry and elegance, trusting beauty to reveal nature's secrets. As our theories grow ever more abstract, Dirac's conviction remains a quiet force. The equations we write shape the universe we see, reminding us that even now beauty is a compass pointing forward.